days, it was all about juice, wasn't it? If you had a large chip in your design, you probably needed quite a bit of juice. You'd stick on a big old power supply in the box, a fan or two, a regulator, and maybe some jumper cables, just to make sure you pumped in enough juice. And zap! Your chip would just light up and go. Power problem solved. Time to get back to the fun digital part of your design. Lately, though, this juice method has started to fall short. Take Altera's Stratix V FPGAs, for example. These are some of the most sophisticated FPGAs ever made. And, as you might expect, you just don't plug in a power and ground with some 4-gauge wires, throw in a Frankenstein-style knife switch, and let the sparks fly. It turns out you have to actually design the power system for your FPGA. Lame. It turns out that getting all the voltages with the right tolerances to the right rails to the right pins at the right time is complicated enough to cut your after-work golf time. Hi, I'm Amelia Dalton, host of Chalk Talk. Getting the right power to your FPGA has gotten a lot more complicated, but it doesn't have to mess up your day or cut in on your golf time. My guests today are Jordon Inkeles of Altera and Sharad Khanal of Linear Technology, and I'm going to talk with them about pairing Altera's Stratix V FPGAs with Linear Technology's power modules for a clean, robust, reliable power solution. Before we get started, I want to remind everyone that you can click on that Download Now button below your player. There you can download a free white paper that further expands on this topic. Welcome, Sharad. Thank you so much for joining me today.
It's great to be here, Amelia.
And welcome, Jordon. Thank you so much for joining me as well.
Hi, Amelia. Great to be here. So, Amelia, today we're going to talk about power management for Altera Stratix V FPGAs. As process geometries get smaller and smaller with each node, typically your power drops on the FPGAs. This typically leads to more sophisticated power distribution networks, including multiple power supplies and tighter tolerances.
Okay, Jordon, before we jump into the details of power management, tell us a little bit about the Stratix V FPGAs.
The Stratix V family is based off TSMC's high-performance 28nm process. It's optimized for high performance and low power. It's an ideal choice for devices in your next-generation high-bandwidth systems. We offer 35% higher performance than alternative process options and 30% lower total power versus previous generations.
Okay, great. So you mentioned bandwidth. Can you tell us a little bit about how Stratix V delivers bandwidth?
Yeah, Stratix V FPGAs are really built for bandwidth from the ground up.
Okay.
They offer the highest bandwidth in the industry. We have 66 transceivers up to 14.1 gigabits per second, which are the highest in the FPGA industry. We also have devices going up to 28 gigabits per second transceivers, including a full spectrum of DDR3 memory, also supported PCI Gen 3,
okay,
variable precision DSP blocks, and fractional PLLs for precision on-die frequency synthesis.
So Stratix V devices aren't all the same, correct? They come in several flavors, am I right? Depending on what you want to do?
That's exactly right. So the Stratix V family really breaks down into 4 different variants.
Okay.
The first is the GT. They have the 28 gigabits per second for very high performance, ultra high bandwidth applications. The next is the mainstream family. This is the GX family. They have up to 66 transceivers that go all the way up to 14.1 gigabits per second. This is great for the Fiber Channel 16 specification.
All right.
And then we have the Stratix V GS variant. These are optimized for high performance, high precision DSP applications and have plenty of memory and DSP performance. Finally, we have the Stratix V E variant. These are our highest density and highest performance.
Does Altera have any power estimation tools that help determine my power needs for Stratix V FPGAs?
Absolutely. They have lots of power tools to help you. First, within Quartus, we have the PowerPlay Power Analyzer.
Okay.
This is a tool within Quartus. However, many folks want to get started earlier before they have either part or all of their design done. In this case, we have the Early Power Estimator. This is called the EPE. It's in an Excel format and is available to download on Altera.com. You simply put in the different utilizations for both logic, RAM, DSP, and so forth, and it will give you a really good approximation of the power that your design will draw, as well as the power supply you need, the currents for each of your power supplies.
Great. So to power up Stratix V, I just hook up a power and a ground pin and I'm all done, right?
I wish it were that simple. 28 nanometer FPGAs have multiple power and multiple ground pins that provide all the power needed to drive one of these FPGAs. But thankful enough, we have the pin connection guidelines that shows in detail what each of the ground pins connect to, the different voltages that are needed, including the tolerances, and which rails can be tied together and which not, depending on what performance you're running at.
Okay, so let's bring Sharad Khanal in from Linear Technology into the discussion here. These guys make a living powering up FPGAs. I understand that Linear Technology and Altera work quite closely together. What other considerations do we have to think about when powering up Stratix V FPGAs?
That's right, Amelia. Designing for low voltage, high current regulators requires special considerations to ensure a robust design. When you're at 0.85 volts, 0.9 volt core voltage and drawing more than 20 amps, you have a very, very tight regulation window to be in. Here is a good overview of the several aspects that impact the accuracy of a voltage regulator. You have the DC error, the switching ripple, and the AC transient ripple.
So Sharad, you mentioned DC error. What is that?
So there are several factors that make up the DC regulation error. You have the reference voltage accuracy, the feedback resistor divider accuracy, the loads and line regulation, as well as the PCB drop, or the interconnection resistance between the power supply and the FPGA that introduce voltage droops.
Okay, let's talk about those one at a time. Let's talk about this VREF first.
Reference voltage in a power supply is the reference that the power supply uses to compare the output voltage to its internal reference. These reference voltages can be spec'd anywhere from 0.5% to 1%, and ideally for a low voltage high current design, we want to choose a part that has a very, very low spec tolerance. We also have to be careful to choose a part that is specified over the full temperature range, so the voltage does not deviate beyond the spec.
Okay, so what about resistor divider error?
Right. Normally people use 1% resistors to set the dividers that set the output voltage. For a more accurate output voltage, people can use 0.1% or 0.5% tolerant resistors to increase this accuracy.
All right, and how about load and line regulation?
The line regulation refers to how much the output voltage changes with changes in input voltage.
Okay.
You want this number to be very, very small because with any change in input voltage, you don't want the output voltage to be affected. The load regulation error refers to how much the output voltage changes as you draw more current from a power supply. Ideally, for these power supplies used for these high performance devices, we want these numbers to be well below 0.1%.
Okay, and finally you mentioned interconnection resistance.
That's right. For a real system on a PC board, you will always have some parasitic resistance between the power supply and the FPGA. Assuming a typical resistance of 2 milliohms, and when you're drawing 20 amps, you'll be drooping up to 40 millivolts, as shown in this example on the slide. If you take that 40 millivolts and divide that by the core voltage of a Stratix V device, you will see that this droop is already over the 3% DC accuracy required for these Stratix V FPGAs.
Okay, so Sharad, how do you deal with that?
The easiest way to deal with this is to sense the power supply voltage at the load. With this, what you do is you eliminate the path between the power supply and the load,
Okay.
and you can account for this parasitic resistance. This slide shows a single-ended remote sensing. So in other words, you're only sensing the VCC in this example, but you're not accounting for any droops between the grounds of these two devices. In the next slide, I will show that by using a differential remote sensing, you can get even more accurate regulation tolerance. In this scheme, you differentially sense between the ground and the VCC pins of the FPGA, and you bring that signal back to the power supply for even more accurate tolerance.
So Sharad, we've done Chalk Talks before on digital power management solutions. How does that play into this?
It plays very well, actually. Digital power management gives you an additional servo feedback loop that helps to regulate these voltages to a very, very tight tolerance. For example, using our LTC2978 PM bus controller, you can get tolerances down to 0.25% by using the ADC and DAC feedback loop. Additionally, these parts also have various other features such as sequencing, monitoring, and also come with a built-in EEPROM, which you can use to store various settings for the system.
Fantastic. So, Sharad, we dove in pretty deep into DC regulation. I understand there is also AC and transient regulation issues that need to be addressed. How do we address those?
Absolutely. That would be a whole nother webcast to cover those topics in more detail.
Okay.
But I want to address two major aspects of AC regulation in this webcast. The first one is the switching ripple, and the second one is the low transient ripple.
Okay, ripple, let's go.
Switching ripple is caused by the inductor ripple current and the ESR of the output capacitors. You can make this ripple smaller by reducing the inductor ripple current or reducing the ESR of the output capacitance network. You can also have high frequency spikes in the output voltage ripple that is caused by layout issues or ringing in the FETs.
Okay, and the load transients?
Right. When you have a load step up, you have a droop in the output voltage because it takes a finite amount of time for the feedback loop of the power supply to respond to additional currents.
Ah, okay.
You also have overshoots when that load gets released from the power supply, and the power supply has to take a finite amount of time to regulate back to the nominal set point. To address switching ripple and low transient ripple, we need a lot more details, and various trade-offs have to be factored in, such as efficiency, switching frequency, number of phases, voltage regulation, etc.
Okay, I think I'm ready to get started. Tell us where we can go for more information.
We have several tools and resources available on our website that you can take a look at and use them to design and verify your solutions. Take a look at the LT PowerCAD and LT Spice software we make available to our customers at no charge, which you can use to design and verify these solutions for Stratix V. We also have a detailed power management guide for Altera FPGAs and CPLDs on our website. We also have several files which link back directly to Altera's website, which show you the power trees used on these reference designs. And finally, you should also check out the Altera development boards and kits page, where you can find more information on these designs to use on actual Altera boards.
Great.
With Stratix V FPGAs in volume production since March of 2012, we have plenty of development kits available in stock today. Each of our development kits, the Stratix V GX, GS, and Signal Integrity Kit, all showcase linear technologies, power solutions available on our dev kits.
All right, well, I think that's all I have time for today. Thank you so much for joining me today, Jordon.
Thank you.
And thank you for joining me, Sharad.
Thank you, Amelia.
And before we go, don't forget to click that Download Now button below the player to download a free white paper that further expands on this topic. For Chalk Talk, I'm Amelia Dalton. For more Chalk Talks, check out the on-demand section of eejournal.com.